Woohoo! Welcome back. Tonight we're going to be talking about rational functions. Yay! And our friend Sharktopus is here to help us because he is smooth and continuous. And although rational functions are not continuous, they do have breaks, they are frequently smooth. So let's get right into it. Now, there are a lot of ways to investigate what it's like to graph something. I would recommend that you use Desmos and play around. Try some graphs. See what happens when you change the inputs. For us, I'm going to suggest we start with the old-fashioned, let's just go ahead and plot some points. So, oh, well, that's a little wiggly. So I'm going to start with x and y, which is equal to 1 over x, and just start with some values. For example, when x is 1, y is 1 over 1, which is 1. If x is 2, y is 1 over 2, which is, well, 1/2. 3, 1/3, so on and so forth. As x gets larger, y is going to get smaller, because that large number is going to get thrown in the denominator. Now, when x is negative, we're going to have 1 over -1, which is just -1. If x is -2, then we get 1 over -2, which is -1/2, and so on and so forth. And so we're going to have very similar things happening on the positive side and on the negative side. Now, here's the downside of plotting points. If this was all I did, I would miss a big part of this graph. So that's why you've got me around, or Sharktopus, or Desmos to help you out. So what I'm going to recommend is that we take a look at the fact that there's actually a very problematic point, and that is what happens when x is 0. That makes y 1 over 0, which is undefined. So we cannot graph this point. This point is not part of the domain. And so it's going to be very important for us to take a look at what happens near 0. Now, is 1 or -1, are those close enough? And the answer is not really. And this is because I happen to know what's going to happen when x is 1/2. When x is 1/2, y is 1 over 1/2. And hopefully you remember when you've got a fraction inside a fraction, that's called a complex fraction, you flip the bottom, basically the bottom fraction flips upside down. So we actually get 1 divided by 1/2, which is 1 times 2 over 1, which is 2. So it actually just flips it upside down. And in the same way, when x is 1/3, y would be 3. So it's kind of cool because what's happening here when x is 2 and y is 1/2, or x is 3 and y is 1/3, the opposite or the reverse thing happens for x. Now, in a perfect world, I would run you through, we'd have a lot of points here. But so that this video doesn't get too long, I'm going to go ahead and show you what happens. And again, you could look in Desmos as well. I've got my x and my y. And what I'm going to do to make it a little easier, let's see, I think I'm going to count by 2s. Just give myself a little bit more space. And I'm going to do it, oops, well, that wouldn't work. 1, 2, 3. I will do it for the x and the y. I'm going to keep the scale the same on the x and y axes, and that way I won't get a graph that got squished in a funny way. If I can count. Right, this does depend on counting. So, you probably want to have someone nearby, like Sharktopus, who can count. Okay, so let's see. I've got the point 1, 1. I've got the point 2, 1/2. Now, the benefit of this is even though it's going to sit right there on that 2, so I'm going to put this 2 down here, and I'm going to give myself a little bit of space there because I'm going to write put in this point at 2 1/2. And now 3 1/3. 1/3, very hard to draw. It's less than 1/2. It's most of the way to 1/2, so it looks kind of like that. And then also I have the point when x is 1/2, y is 2. There's x equals 1/2 right there, and y is 2 is right there. And you'll notice I've got this little swishy guy like that, kind of scooping down like that. Let's take a look at what's happening here. What's happening here in the negatives, and I've already kind of given it away in quadrant 3, -1, -1, which is right here. When x is -2, y is -1/2. When x is -3, y is -1/3. And spoilers, but this has the same, and of course I have the same problematic scale values here because they're in the way, but the same thing that happens when x is 1/2 and y is 2, we get when x is -1/2, y is -2. Now, there are two other things happening in this graph. Let me see if I can get a fun color to use. There we go. I'll grab a red pen. The first thing that's going to happen is x cannot be 0. And when we have a problematic domain point like that, where x cannot be a value at all, generally speaking, we're going to have a little fence there, a little line. It's usually a dotted line. I'm doing it in red to make it a little bit easier to see. This is the point when x equals 0, and this is actually going to be an asymptote. Now, what does that mean? That means what's going to happen, and if we had lots and lots of time to fill this in, we'd go 1/4 becomes 4, 1/10 becomes 10, 1/100th becomes 100. So the correspondence from 1/3 to 3, 1/4 to 4, 1/10 to 10, 1/100th to 100 is going to mean that this graph is going to shoot up and get bigger and bigger and bigger. As x gets closer to y, as x gets smaller, 1/x gets bigger, and so it heads up like this. In the same way, in the third quadrant, when x is negative by getting very close to 0, we end up with a piece of the curve that comes down like this, because for the same reason, except these are all negative. If x is very, very small, then 1/, that very small number is really, really big. We've also got another asymptote. Now, the other asymptote is kind of surprising, but it turns out that y equals 0 is another asymptote. It's called the horizontal asymptote. So I'm going to draw that in. And again, I'm drawing it slightly above or slightly to one side to make it easy to see. Hopefully, that's y equals 0. That's also an asymptote. And why is that? Well, if you've got the equation f of x equals 1/x, so y equals 1/x, can y be equal to 0? And the answer is no. Y cannot be 0. Why can y not be 0? The answer is 0. If you've got a fraction, the only way to create or set it equal to 0 is for the numerator to equal 0. So can this be 0? And the answer is it can never be 0, because if a/b equals 0, then a has to equal 0. The numerator has to be 0. And so y can never be 0, no matter how big x is. And here's the other way to think about it. If x is 1 billion, 1 divided by 1 billion, if you have one pizza and you're going to try to feed 1 billion people, everybody's going to get a real small piece, right? But technically it's not 0. You still get an atom or 5 atoms, maybe if you're lucky. And so probably way more than that. I have no idea. But 1 over a billion is not 0. It's a very small number, but it's not 0. So what happens here? Well, here this gets, as you divide that one pizza into as many pieces as you need, the amount each person gets smaller and smaller and smaller, but never actually gets to 0. The same thing happens over here. It gets technically larger and larger because it's negative, gets closer and closer to 0 as x gets more negative. And that's our graph. That is the graph of 1 over x. And so the question is, let's try graphing. After you've graphed this, let's try graphing 1 over x minus 2. And I've got a hint down here that I want to make use of. How can this graph be seen as a transformation of f of x? So f of x was the first one we just did. If we go from 1 over x to 1 over x minus 2, well, that should just be a transformation, right? That should be a transformation that shifts the original graph 2 units to the, and then you got to think about it. Does it shift it to the right or to the left? If you're subtracting 2 inside the function, you're changing x, not y. And so you end up with the opposite effect. So if you're subtracting 2 from x, it shifts the original graph 2 units to the right. Now, how could we guess that without even thinking about the transformation? Well, if we've got g of x is equal to 1 over x minus 2, and we say, what is the domain? Well, we would say, oh, don't let x equal 2, right? Just like up here, the domain was don't let x equal 0. So if x cannot be 2, then we just take this asymptote and shift it over. So let me get my basic graph in. There's y. There's x. There's 1. There's 2. There's 3. So here, I would just have my vertical asymptote move over. Let me scooch this up so you can see it. I would move my vertical asymptote over to x equals 2. So the whole graph shifts to the right because this is the value that x can't be. Now let's check this. Let's go ahead and use, you can always use plotting points to figure out if what you suspect is true is really true. So let me try plugging in just like I did above there. When x is 1, I've got 1 over 1 minus 2. That's 1 over negative 1, which is negative 1. When x is 2, that's not allowed. When x is 3, 1 over 3 minus 2, that's 1 over 1, that's 1. When x is 4, 1 over 4 minus 2, that's 1 over 2, so that's 1/2. Okay. So let's look at these values here. So for 1, if x is 1, y is negative 1. So I got a point right there. 2 is not on the graph. 3 is the point 1. And 4 is the point 1/2. Okay, so far so good. We may want to graph some more points. For example, let me try what happens when x is 0. I get 1 over 0 minus 2, that's negative 1/2. At 0 is negative 1/2. And can I convince you that this looks a lot like right there and right there, these two parts, and our graph actually looks something like this, because it is just a right shift. So we took this whole graph and we shifted this to the right 2 units. If we shift something 2 units to the right, does that change? Does that move anything up or down? And the answer is no. So our other asymptote is still here at y equals 0. So x equals 2, y equals 0. These are the asymptotes. Just like that. Those are the fences, effectively, for this particular graph. And we've got it done. Woohoo! Woohoo! Yay! Okay, in our next video, more of this. Yay! But remember, if you have questions, if I said something didn't make any sense, if you want to ask more questions or you just want to check about some of the stuff I said, or you just want to say hi, please feel free to contact me or the tutors. And remember to hydrate, get yourself a nice yummy snack, and I will see you back in the next video where we will graph yet more of these rational functions. Woohoo! So yay, woohoo, math on.